Good evening and welcome to your second flip classroom. So just to recap, your carboxylic acids are going to have that carbonyl group, which is your carbon double bond to your oxygen, and they're also going to have an OH group attached to that carbon. So because the carboxylic acids are acids, it's literally in the name, they undergo similar reactions that you would expect your acids to undergo when they're reacting with your bases, your carbonates, and your reactive metals. However, it's important to note that they're weak acids. We looked at a few examples of some of your common carboxylic acids, your metanoic acids. So in addition to your alkyl carboxylic acids, you also have your aromatic carboxylic acids. So this is where you're going to have that double bond oxygen along with your OH group attached to the carbon within your benzene ring, which is your aromatic ring. Now when it comes to these type of carboxylic acids, we just looked at your alkyl carboxylic acids. You also have your aromatic carboxylic acids, and these are your examples where you have your carboxylic acid group attached to a carbon within your benzene ring, which is considered your aromatic ring. So if it's on the 1 and 2nd carbon, it is denoted by your ortho or O. Your 1 and 3rd carbon is denoted by your metal or M, 1 and 2, 1 and 3, if your substituents were on the opposite sides. And lastly, you have your 1 and 4, which is your para location or your P. So here are some examples of your aromatic carboxylic acids. You have your carboxylic acid group and the respective substituent. So here you have your chloro. So it's on the 3rd carbon, so it's your 3-chlorobenzoic acid or your metal chlorobenzoic acid or your M, which represents your metal. And then you have your P for your para or your 4th position on your benzene ring. So we went through naming these carboxylic acids in class. The first one was your ethanoic, the second one was your 2-methyl propanoic acid, and your third one is your 2-bromobenzoic acid or your O or your ortho bromobenzoic acid, because your bromo group is on the 2nd carbon. Lastly, we looked at the preparation of your carboxylic acids. When we looked at your previous alcohols topic, you would have looked at the oxidation of your alcohols, and it was noted that your primary alcohols, when they undergo oxidation with your respective oxidizing agents like your potassium dichromate or your potassium permanganate, they would produce aldehydes, which can be further oxidized to your carboxylic acid. So here we just have an example of your primary alcohol, ethanol, oxidized to your ethanol, and then oxidized to your ethanoic acid. So this is a learning check where you're asked to note what alcohol could be used to prepare the following. And you have your butanoic acid, and in question 2 you have your propanoic acid. Again, we're looking at your primary alcohols. So the first one would be your butanol or your butan, and 1-ol, your propanol, which under your IUPAC is gonna be your propan 1-ol, to give you the position of your OH/your alcohol group. So this is just giving you back your carboxylic acids, but just starting off with your respective alcohols. So you have your butan 1-ol, oxidized your aldehyde, your butanol, and then you get your butanoic acid, and the same is done for your propan 1-ol. Now we're going to be looking at the properties of your carboxylic acids. Your carboxylic acids exhibit polarity, and that polarity has to do with these dipole moments here, partial negative to partial positive charges. Dipole moments are the distribution of charges occur when you have a more electronegative atom. So there are 2 groups, your hydroxy group here, and then you have your carbonyl group here. In both cases, you have your very electronegative oxygen that is pulling the electron density towards itself and is carrying that partially negative charge. So that leaves your carbon along with your hydrogen with a partially positive charge. So this difference in electronegativity gives you those dipole moments that causes your carboxylic acids to become very polar. An additional property of a carboxylic acid also has to do with these two polar groups. You had your carbonyl group and then you had your OH group. So the presence of these two groups allows your carboxylic acids to form dimers, essentially where they're forming hydrogen bonds with another carboxyl group. The ability to form dimers allows your carboxylic acids to therefore have high boiling points compared to other substances of similar molar mass, and this has to do with their tendency to form stabilized dimers through hydrogen bonding. Again, for hydrogen bonding, this is looking at bonds between your oxygen to your hydrogen, nitrogen, or your fluorine, because these are very electronegative atoms. But in the case of your carboxylic acids, you're looking at your hydrogen or your OH. So this is one carboxylic acid here, and this is the other one. So these hydrogens and these oxygens are forming those hydrogen bonds, allowing your carboxylic acids to form dimers. Your carboxylic acids are weak acids and can undergo these similar reactions. So because they're weak acids, they are going to partially ionize in water. Carboxylic acids ionize in water to produce your carboxylic ions and your hydronium ions. Your acids are proton donors, so this H is lost from your acid and donated to your water molecule to form your hydronium ions and lands you with your carboxylate ion. Now we're going to look at the different types of reactions that your carboxylic acids undergo. Reactions with your sodium hydroxide, this is going to give you your salt and water. Undergo reactions with your sodium hydrogen carbonate. This is going to produce your carbon dioxide gas. It can react with your metals to give you hydrogen gas, and it can react with your alcohols to form your esters, and this is known as your esterification. And lastly, they have reactions with your phosphorus trichloride, your phosphorus 5-chloride, and your thionyl chloride. Your carboxylic acids react with your sodium hydroxide, and this is going to give you your salt, which in this case is your sodium ethanoate and your water molecule. They can also react with your reactive metals such as your sodium, and this is going to produce your salt again, but you have the addition of your hydrogen gas. So one of the questions that we're going to be looking at on Wednesday would be this one. So you're going to write an equation to show the reaction of your butanoic acid with magnesium. We're going to have your butanoic acid here, and instead of your sodium you have your magnesium, and this is going to give you your magnesium butanoate salt and your H2 gas. So you're just going to write out that equation and name the salt. So next, your carboxylic acids can react with your carbonates and your hydrogen carbonates, right? So in both of these cases, you're going to be forming, right? So your first two examples are your ionic equations, where you just have H plus from your acid and your carbonates or your hydrogen carbonates, right? It's going to give you your water and your carbon dioxide gas. Your second question is going to come from your ethanoic acid reacting with your sodium carbonate. This is going to give you your salt, your water, and your CO2. Good question for Wednesday. Ethanoic acid is also known as your enantic acid. So you're going to get a similar answer to this one. Right, so you're going to write equations for your ethanoic along with your heptanoic acid. So now we're going to be looking at your carboxylic acids reacting readily with your phosphorus 3,5-chloride and your thionyl chloride, right? So carboxylic acids react readily with these examples to produce your acid chlorides, which are also known as your acid chlorides, right? So these reactions are going to be producing your white fumes of your hydrochloric acids. So here we have your carboxylic acid reacting with your phosphorus 3 chloride, and this is going to give you your acyl chloride or acid chloride and your phosphorus acid. And heat is required for this particular reaction. In a reaction with your thionyl chloride, you are also going to be getting your acyl chloride or acid chloride, HCl, or your white fumes, and your sulfur dioxide gas. And for this particular reaction, no special conditions are required. So in all of your examples, your acyl or your acid chlorides were being produced. So now we're going to look at what exactly your acyl chlorides are. Acyl chloride is similar in structure to a carboxylic acid, but your OH group is being replaced by a Cl atom. This electron withdrawing group is going to be pulling the electron density towards itself, making your carbon more partially positive. So this is going to make it more susceptible to your nucleophilic attack. All right. So here you have the mechanism for a nucleophilic attack of your acyl chloride. So again, this is electron withdrawing, giving your carbon that partially positive charge. Your oxygen, which is also electronegative, is now partially negative. So it's pulling electrons within this bond towards itself, breaking that double bond there. Your electronegative chlorine causes your carbon to carry that partially positive charge. Your electronegative atom is now pulling electron density towards itself, breaking that double bond, while your nucleophile can now attack / form a bond with your carbon. Right? In addition to that, completely breaking the bond between your carbon and your chlorine. Once this bond is broken, your carbon can then retain back its full bond by forming that oxygen double bond here, and your free chlorine atom will then pick off a hydrogen off of your water molecule and eliminates HCl. Now we're looking at how your carboxylic acids can react with your alcohols to form your esters, and this process is known as your esterification, right? And it is also a condensation reaction, meaning you're gonna be excluding out a small molecule, and that small molecule is gonna be your water molecule, right? So the conditions necessary for this reaction to occur are going to be your catalyst. The catalyst is usually an acid catalyst, so you're either going to see the full acid or you're going to see an H plus in your reaction equation. Alright, so you have your acid catalyst, and then your reactants are heated under reflux, and then your ester is distilled off. When it comes to naming your esters, when naming your esters, you're going to start with your alkyl group from your alcohol, which is at your right hand side of your oxygen, and everything else is going to give you the remaining name for your esters. So in this case, you have your methyl, 1, 2, 3, 4 butanoate. Second one, you have your ethyl, and 1, 2, 3. So this is going to be your ethyl propanoate. So then to add to these two would be your practice questions in preparation for your next topic. So when we come on Wednesday, we're going to be looking at the diagram with the missing blocks and the two individual equations. I'll put it at the end. So along with your in-between equation questions, you have this diagram here that shows you the products formed when your carboxylic acid, in this case your propanoic acid, reacts with the reagent shown. So it's just the same reactions that we were previously looking at. So you're going to have your phosphorus 5 chloride react This is your reaction with your carbonates, particularly your calcium carbonates. So you have your reaction with your base, you have your reaction with sodium hydroxide, you have your reactive metals, have your alcohol, and that's gonna give you